We are going to start the application of a new model today, and we are just going to continue next week from the point that we have left. Most probably this is going to be the last application that we are going to develop, and it is going to take a very long amount of time, and it is a quite complicated application because it is going to be mentioned in the next chapter of our textbook. So this is the chapter that we are going to cover, chapter 5, in the remaining parts of the arena classes. So we are going to describe a system here, which is called a simple call center system. And we are going to apply the simulation model of this. Now, this is a quite hard system to understand. And unfortunately, I'm not going to be able to draw a flow chart. So you need to read this description again and again. I mean, when you are studying at home tomorrow, until tomorrow, for example, it is a good idea if you study this system. It's a simple call center system, and let's read it. Let's read the details and try to understand it as much as we can. And today we are just going to come up to a point where we will be modeling in modeling of this system, and tomorrow we are going to continue from the point where we have left. So let's read. Or generic call center system. So this is a call center system. So you know the call centers, the customers are calling to get a service from a client to the customer representative. Okay. So we have representatives in the other side of the lines, and they are going to help us in order to perform a task. Okay. So we have a call center system that provides a central number in an organization that customers call for technical support, sales information, and order status. So this is the first sentence that we need to understand. So people are calling this call center for three different issues. So they either want to get a technical support, they either want to get a sales information, or they want to learn about the status of their orders. Okay, there are three issues that they are calling for. So there may be one of these three, it can be one of these three different issues. Incoming calls arrive with inter-arrival times being exponentially distributed with a mean of 0.857 minutes. So the customers are making calls with an exponential inter-arrival time of 0.857 minutes average. So this means what? This means the arrival process is a Poisson process. Okay, please be careful to understand this here. If the inter-arrival times are exponentially distributed, then the arrival process is called a Poisson process. This central number feeds 26 trunk lines, it says. So we have 26 trunk lines. If all 26 lines are in use, a caller gets a busy signal. Hopefully the caller will try again later, but for our model, just go away. So it says what? If a caller calls, but at that point, if 26 clients are in the system, if 26 clients are available in the system, then that caller is just going to turn off the phone, and then maybe we'll call again later. But at that point, we will assume that that caller is going to immediately leave the system. So the capacity of this total system, the whole system has the capacity of 26 callers. Okay, so there are only 26 lines that are available. If all these 26 lines are busy, in that case, the caller gets a busy signal and will leave the system immediately. An answered call, I mean, if somehow you find one of these trunk lines available, in that case, an answered caller hears a recording describing three options: transfer to technical support, sales information, and order status inquiry. Okay, so you need to listen for a recording, and when you listen to this recording, the estimated time for this recording is uniformly distributed between 0.1 and 0.6 minutes. Okay, continuously and uniformly distributed between 0.1 and 0.6 minutes. If the caller chooses technical support, now for every type of color, we will have a different process. If the caller chooses technical support, a second recording requests which of three product types the caller is using, which requires uniformly distributed amount of time between 0.1 and 0.5 minutes. The percentage of requests for product types 1, 2, and 3 are 25%, 34%, and 41% respectively. If a qualified technical support person is available for the selected product type, the call is automatically routed to that person. If none are currently available, the customer is placed in an electronic queue where he is subjected to annoying rock music until a support person is available. The time for all technical support calls is estimated to be triangular with 3 minimum, 18 maximum, and 6 most likely duration amount in minutes, and regardless of the product type. Upon completion of the call, the customer exits system. Bu görüşme tamamlandıktan sonra diyor müşteri sistemi terk ediyormuş. İkinci prosese bakalım. Sales calls are automatically routed to the sales staff. If a salesperson is not available, the caller is treated to soothing D-Wave space music. After all, we are hoping for a sale. Sales calls are estimated to be triangularly distributed with minimum amount of time of 4 minutes, maximum amount of time of 45 minutes, and most likely time of 15 minutes. Sales people tend to talk a lot more than technical support people. Upon completion of the call, this happy customer exits the system. Callers requesting order status information are automatically handled by the phone system, and there is no limit on the number of system can handle, except that there are only 26 trunk lines, which is itself a limit since an ongoing order status call occupies one of these lines. The estimated time for these transactions is triangularly distributed, again with 2, 3, 4 minutes, with 15% of these callers opting to speak to a real person after they have reached their order status. So these calls, these 15% of the calls are routed to the sales staff, where they wait with a lower priority than sales calls. This means that if an order status call is in queue waiting for a salesperson and a new arriving sales call enters, the sales call will be given priority over the order status call and answered first. These follow-up order status calls are estimated to last triangularly distributed amount of time with minimum 3 minutes, maximum 10 minutes, and most likely time of 5 minutes. These callers then exit the system. The call center hours are from 8 a.m. to 6 p.m. with a small proportion of the staff on duty until 7 p.m. Although the system closes to new calls at 6 p.m., all calls that enter the system by that time are answered and served. Over the course of a day, there are 8 technical support employees to answer technical support calls. 2 are devoted to product type 1, 3 to product type 2, and 3 to product type 3 calls. There are 4 sales employees to answer the sales calls and those order status calls that opt to speak to a real person. As a point of interest, we'll count the number of customer calls that are not able to get a trunk line and are those rejected from entering the system. Similar to bulking and queuing systems, though bulking usually means a decision on the customer's part not to enter rather than being rejected as in our model. However, we won't consider reneging customers who get a trunk line initially but later hang up the phone before being served. Some statistics of interest for these types of systems are number of customer rejections, total time on the line by customer type, time waiting for a real person by customer type, number of calls waiting for service by customer type, and personal utilization. The first issue that we need to use is customer rejections and bulking. So how are we going to implement bulking? How are we going to disable the entrances of customers who cannot find a trunk line? So when the system is full with 26 entities in the system, a new coming customer will not be able to enter the system. So how are we going to apply that? Another issue that we are going to use is three-way decisions. So you see there are 3 types of customers. There are 3 types of products. So up to this point, we have used decision modules on only two-way modeling. So this time we are going to apply a three-way decision modeling. And again, in these modules, we are going to use some system variables and expressions. So these issues are new issues that we are going to learn in this application, and how we are going to use them. The variables are different than the attributes, okay? Attributes are labels that are attached on the entities, but the variables are belonging to the system. They are called system variables. So the variables are somehow created with a similar manner as attributes, but the attributes are belonging to the entities, but variables are belonging to the whole system itself. And we are going to define expressions in this application, and we are just going to use the storage concept, which is a similar concept like queue, but it is called storage. And we are going to explain why we are going to use the storage, and we are going to determine how we are going to terminate a replication of this simulation. Okay? So there are two types of simulations. The first type of simulation is a terminating simulation, and the second type of simulation is a steady state simulation. A terminating simulation ends, a replication in terminating simulation ends when a certain event occurs, okay? A certain event, for example, in the end of the day, after 6 p.m., if all customers leave the system will terminate. So that day is going to terminate. So these kind of simulations are called terminating simulations. A certain event describes the ending of the simulation. In steady state simulations, in fact, we run the simulation for a very, very long amount of time. There is not a terminating event. So we do not wait the system to terminate. Instead, we observe it for a long amount of time. Okay? Now, this example here is a terminating simulation. Why? Because there is a terminating condition. What is that condition? There are two conditions for termination. First of all, the clock needs to show 6 p.m. Okay? And the second condition, after 6 p.m., all of the work in process clients, all of the clients that are in the system should leave the system after getting the service. So if these two conditions are satisfied together, the system will terminate, the simulation will terminate. So this is the terminating condition of this simulation. And we are going to follow this modeling approach page by page, okay, page by page. And we are going to see, as you can see, we have different sections here. So from section 5.4.1 to 5.4.6, we are going to run all of these sections one by one. Okay, we are going to create our model with each step. Okay,